Okay, so today we're going to do Boyles Law, which is on page 92 of your textbook. It's a very short and easy section, and you can get marks easily from this section. Now, this is one of the gas laws that you get, and it focuses specifically on the relationship between volume and pressure. Okay, so Boyle's law is all about how volume and pressure are related to each other. Now, the definition of Boyle's law, which is something that you must know of by heart, is the volume of an enclosed mass of gas is inversely proportional to the pressure when the temperature is constant. Now, there's three things you need to know here. The first thing is volume and pressure are inversely proportional, so that's the relationship between them. Okay, but this is only true when temperature remains constant, which means if temperature is not constant, you're not going to be obeying Boyle's law. So Boyle's law is basically volume and pressure are inversely proportional only when the temperature remains constant. Now, it's very important that you learn this definition as is, because if you leave out, for example, the part of the temperature, then you're not going to get the full marks in an exam or test. Okay, now if you write this in formula style, it will be volume is inversely proportional to pressure, or it's the same thing as saying pressure is inversely proportional to volume. It's exactly the same, but both of this is only true if temperature is constant. Now that makes sense if you think about it. For example, if we're talking about a syringe, like an injection, right now when you press that thing down on top of the syringe, you're actually putting pressure on it, and as you putting pressure on it, putting it downwards, the volume inside the syringe is getting small. So the more pressure you put, the smaller the volume is, which tells you as pressure is increasing, volume is decreasing. And if you open that thing of the syringe or injection, or you lift it up, now you are making pressure less, because now obviously you're not putting any pressure, you're actually decreasing the pressure. And as you're doing that, the space inside of the syringe is becoming much bigger. That shows that as you're increasing pressure, volume is decreasing, and as you're decreasing pressure, volume is increasing. So it's inversely proportional to each other. Now, if you have to draw a graph of volume versus pressure, which is like the one on page 93, you'll get a graph that looks like this. So you have volume and pressure on the x-axis. You could even change it upside down. You could put pressure on the y-axis and volume on the x-axis. It didn't really matter. But either way, you will end up with a hyperbola or a curve graph that is decreasing, which shows volume and pressure decreasing as you're going along. Now, most of the time in physics, we like to make graphs to be a straight line graph. And as you see here, this is definitely not a straight line graph. So the way we convert it into a straight line graph is like this. Now, when you write something like that, V is, you put this proportional sign, and then you say 1 over P, or same as P is inversely proportional to 1 over V. It's always the 1 on top, and every time you see this 1, it means inversely proportional. Now there's two ways at looking at this here. If you see the 1 over P, it's like saying volume is inversely proportional to pressure. But there's also a second meaning to it, which means that volume is directly proportional to 1 over pressure. So there's two ways of looking at this 1 over something. It's either you can say it's inversely proportional, or you can say volume is directly proportional to 1 over pressure. And the same thing here. You can either say P is inversely proportional to volume because of this 1, or instead of saying inversely proportional, you can say P is directly proportional to 1 over V. So that 1 over V or 1 over P actually becomes something which you're saying it's directly proportional to. So if you look at it at that way, making it directly proportional instead of inversely proportional, then it's easy for you to get a straight line graph. So now, if you plot volume versus 1 over P, not P anymore, now we're looking at 1 over P, then you will get a straight line going through the origin. And anytime you have a straight line going through the origin, that tells you a directly proportional relationship. Okay, so anytime you see straight line growing through the origin, it means directly proportional relationship. So here you can only get a straight line if you're plotting volume versus 1 over P. Or you can even change it around. You can even say pressure is inversely proportional to 1 over V. Either way, because you're saying directly proportional to 1 over something, now you get a straight line graph. So let's look at the difference between the two. So can you see here? The first graph, you have volume versus pressure. That's why you have a curve graph. The second graph, instead of having volume versus pressure, now you have volume versus 1 over pressure. And that 1 over pressure makes a huge difference, that the graph now becomes a directly proportional graph, which is a straight line going through the origin. Now, taking all of this into consideration, if you put Boyles law in an equation or formula form, you get this formula, which is P1 V1 is equals to P2 V2, and this here is Boyle's equation, and we use this equation if we want to find out pressure or volume in a certain kind of situation. And can you see that we have P1, P2, V1 and V2, so we have 2 pressures and 2 volumes. So P1 and V1 is like the initial or before or the first one, and P2 and V2 is the final or the after. Okay, so when you're using this Boyle's equation, you need to either have 2 volumes or 2 pressures and one of the other one, so that you can calculate this other one here. And then from this, we also get that if you multiply pressure and volume to each other, that will equal to K. Now, if you ever see a small k in physics, it means it's a constant. So if you multiply pressure times volume, you will get a constant value. Now, let me show you an example of this here. If you go back to your textbook on page 92, can you see that you have this table here with volume, and then you have pressure, and then you have 1 over pressure. Now, let's look at volume and pressure. Can you see as you're going down the table, volume is increasing. It's going from 15, 20, 23, and then it's ending at 50. But as you're going down, let's look what's happening to pressure. Can you see that pressure is actually decreasing? It started from 200 and now it's moving on to 60. So as volume is increasing, pressure is decreasing. Now, if we take these 2 columns, which is volume times pressure, and we multiply them to each other, can you see we have them here in the last column here? You have PV. So you have volume times pressure, and then this whole column here, can you see you have the same exact number, which is 3 times 10 to the power of 3 joules. It doesn't matter what the volume and the pressure is. When you multiply the two, you're going to get a constant number, and that constant is what we call K. So this here just shows you how PV is equals to K. So it doesn't matter any pressure and volume, if you multiply them together, you'll get a constant number. Okay, now you can go back to your textbook and you can read all about how volume and pressure is related when the temperature is constant. And from the previous section, which I told you to make a summary of, it showed here that if you have a real gas, it deviates from an ideal gas at high pressures and low temperatures. Now, if you look here at this graph here, you don't need to know it too much, but just so you're aware of it. Can you see that the green graph shows you ideal gas? Now, ideal gas is something which is not real. It's like a perfect gas that follows perfect laws, but obviously nothing is perfect in real life. So this is just an ideal gas, how it should be if it's ideal. And here's the graphs for each of them: volume versus pressure, volume versus 1 over pressure. And then if you have a real gas which is real and it doesn't follow perfect laws, then you will get this red graph which doesn't go exactly how you want it to go, but it follows the same pattern. So it still shows that volume and pressure is inversely proportional, and if you plot V versus 1 over P, you'll get a straight line graph showing directly proportional of V and 1 over P, but it's not going through the origin exactly. And this is because real gases deviate from ideal gas behavior at high pressures and low temperatures. Okay, now this section is very easy, and it's also similar to the sections we're going to be doing afterwards, and it's an easy way to get marks. And all you have to do is mostly calculations and know the relationships between pressure and volume and other things which we will see later on, and also know how to use these equations. Right, so the best way, let us go straight into examples. Right, let's look at this first one. It says here, the volumes and corresponding pressures of a certain mass of dry air at a constant temperature. Can you see the temperature is constant, which means Boyle's law will be obeyed, because at constant temperature, pressure and volume are inversely proportional. Right, it's given in the following table. So we have a table here with different volumes, different pressures, and P times V, which is PV. Right, now we know that when you multiply pressure and volume, this is going to give you a constant number. And can you see that all of these numbers are constant? They are all 1200. So it doesn't matter if you're changing the pressure or volume. Once you multiply them to each other, you will get a constant value. Right, now they're asking us to calculate the volume of this mass of air at a pressure of 15 kilopascals. Okay. So remember, when you're using Boyles law, this is the formula: P1 V1 is equals to P2 V2, which means you're going to need two pressures or two volumes and then one of the other one so that you can solve for whatever they're asking you to solve for. So here they're asking you to solve for volume, which means we need to have two pressures and one volume, and the other volume, which is what we're going to solve for. Now, the beauty of Boyles law is that you don't need to worry about units. Normally, volume is always in decimeter cubed, isn't it? And pressure, it can either be in kilopascals, atmosphere, or whatever pressure is measured in. Now, with Boyles law, you don't need to worry about units, and this is the first time in chemistry and physics that you don't need to care about units. As long as the units are the same, it means they will cancel out, so you don't have to convert anything. You just have to make sure that P1 and P2 have the same units, and V1 and V2 have the same units. And if both of them have identical units, then it will cancel out, so you don't really need to convert anything here. So that's a nice thing. Okay. Now, there's two ways you can do this. You can either use this formula here, P1 V1 is equals to P2 V2, or you can use P1 V1 is equals to K, because now they're giving us K in this column here. Right, now I think it's much easier to use this one here, so let's go straight into this. Now, obviously, we're solving for V, and P, they gave it to us, it's 15 kilopascals. So all we have to do is substitute now. So P will be 15 kilopascals, and K, which is from the table, is going to be 1200, and that will give you 80 centimeter cubed. Now, can you see we didn't change any units? I didn't change pressure, I didn't change volume, because it really doesn't matter, it will cancel out. If you want to use this formula, then you're just going to choose any set of values here for V and P, and you just need to substitute it in and you'll get the exact same answer. So it's very simple. All you have to do is look at the formula, which is Boyles law, substitute the numbers in it, and then solve for your answer, and that's how you get 3 marks. Okay, let's look at example 5.